all of you. So do we have everybody? Can you guys hear me? All right, cool.
Yes, Doctor.
Right, I've uploaded the slides in your e-learning, and I also have give some self-study assignments, so you can look through later for the self-study. So actually, but last night when I was preparing for the lecture, I came across a book that is really suitable for this class. I mean, for the whole class. I mean, the whole syllabus. And it can be the main reference. I've been searching for one textbook that can be used as our main reference. But not until last night, then I saw this book and I changed my slides. I have my slides prepared, but I changed my slide to follow the organization of the book, and resulting that I most of the content of the slides are being copy pasted from the book. So please do not share my slide because if it goes out there, it will be plagiarism. So this is just for you guys to study, right? So I'm using all the sentences in the book on my slide. So just to give you a heads up so that you are aware that you cannot share the slides with anyone. Just within yourself, within this class only. Right, so let's begin then. And the book, the book, I have also uploaded the PDF of the book. So, but unfortunately, the previous slides, the previous notes for previous topics were not based on this book. So it was taken from the previous topics was taken from different sources. So the best is that you keep for previous topics you can study the slides rather than finding points in the sources, because I have taken it from everywhere. I combine the information, so the slide will be sufficient for you to study. For this topic, the content are similar to the slide contents are similar to the book content. So it's okay to read the book for further understanding. Right, so let me share my screen now.
Hi, Doctor. Hanisa just informed she's having internet problem and she can't connect to our class today.
Okay, the meeting is the class is recorded. I mean, maybe you can ask from the admin later on the link to all the records for our class.
Okay, Doctor.
Share with Hanisa.
Okay, sure. Thank you, Doctor.
Okay, so you can see my screen, yeah?
Yes, Doctor. Can see.
Thank you. Okay. Alright, so today we are going to look at neuron model, more towards how the neuron model how neurons are being modeled into circuits and later built as later developed as computational neuroscience model. So we will look at a few models and how they are being developed as circuits. Okay, so in this topic we'll be looking at single neuron model and simplified neuron model. In simplified neuron model, there are three models: integrate and fire model, wiki, integrate and fire model, and the Hopkin model. So just a bit of recap: brain, body, and behavior. So the human brain is made of 86 billion neurons, and each neuron is connected to 10,000 other neurons, and 1 millimeter of cortex contains nearly 1 billion connections. So you can see the size of brains. Human brain has the bigger size, so there will be more neurons and more connections. Okay. So to model the brain, what does it mean to model the brain? Is to emulate new algorithms. From by modeling the brain, new algorithms such as deep learning is being produced to heal new therapies, such as deep brain stimulation, and to understand new knowledge, e.g. visual attention. So how to understand how our brain works. So the new knowledge transpire like visual attention. What kind of models that we can come up from studying the brain? We can set models as connectionist models for performances and learning, biophysical models for simulation and prediction, connective models for the emulation of behavior. So what we are going to see today is biophysical models for simulation and prediction. How to build models? The basic material is that the anatomy and physiology of the brain itself, okay, and then the experiments and recording, the pathologies and the lesions. So the basic materials is more related to the sciences, and then it is then integrated by mathematics people and informatics people, and they come up with working hypotheses, which introduce extreme simplifications and build parallel and distributed computing from the modeling of the brain system or any biological system, and also dynamic systems and learning. These are then being validated through prediction and explanation. So how modeling a single neuron. Why do we um, modeling a single neuron? So we know that neuron is an electrical excitable cells that process and transmit information through electrical and chemical signals. A recap. This is your neuron, and we have soma, we have dendrites, we have axon, and we have synapse. Okay, what we are looking at is the axon, where the electrical signals will go through and will be transmitted through the synapse. So this is the recap on the synapse process transmission. You have this a bit different diagram, but the concept is similar. So this is in axon. So inside the axon, it hasn't going towards the synapse. So you can see the axon. You can see it's like a cylinder where it has membrane. So in order for these signals or the ion to go through this to be transmitted, they need to go out of the membrane. So it has the membrane has there should be a what I call the outing like channel or something that is going through the internal from internal to the outer part of the membrane. So this channel is transporting the ions inside and out, going inside and going outside. This is called ionic channel. So the transmission, the electrical entity that we are talking about is actually the ions transmission. So they are the so-called electrics in the nerve system. Alright. So the neuron is an electrical. Okay, this is the thing. So this is an example of excitable system. So this is if you have this kind of input, and this is the kind of transmission that it might do, and this is the output signals that is being recorded. Okay, this and neural circuits uh, is where many neurons work together on a function. So neurons never function in isolation. They are organized into symbols of circuits that process specific kinds of information. So you have afferent neuron, efferent neurons, the neurons are the basic consequences of neural circuits. Okay. So later we'll look at how does this neuron model turn into circuits. Okay. So the early discovery for single neuron, yes, it started in 1840, where Italian scientist Carlo Matteucci found that there were currents flowing from the section of a frog muscle to its undamaged surface, and they call it demarcation current. And then a German physiologist, Emil the priest, I don't know how to say it, ancient Riemann, found that the potential difference between the injured surface and impact surface decreased transiently when a stimulus was given, and this is called negative variation. Uh, uh, the student of the boys Raymond, his student Julius Bernstein continued the study and found that negative variation is transient and its duration is about 1 millisecond and independent of the stimulus intensity. So if the stimulus is strong enough, the variation implicated can have an overshoot, i.e. surpass the filter of resting potential. So you should remember if the action potential happens means the spiking allows the ion to move from the inside of the axon to the outside of the axon through the axon membrane. Okay, so resting potential is when the spiking has finished. However, he observed such phenomenon only in nerves and neglected important fact when he tried to explain the underlying mechanism of action potential. So he focused on the resting potential, but he neglect the mechanism of action potential. Uh, and this phenomenon contradicts his theory. The propagating speed spikes along the nerve is about 28.7 milliseconds, meter meter per second, which coincides with the value estimated by German scientists in 1850 when he was observing nerve muscle compression. Okay, this is what Bernstein observed. So you have they are looking at frog. We are still working on frog, okay, and frog muscle, okay, and they're looking at intact muscle, and also the upper diagram is an intact muscle, okay. So diagram show a muscle that is damaged, okay. So there is a negative charge and positive charge accumulated in the inside and outside of the membrane. So the membrane is the line here, okay, the both line, the both line, the upper and lower bottom line, and these are the um, these are the uh, these are the lines, and these are the positive and negative charge inside the membrane. Okay, and the lower diagram shows that the magnetization is at its left end, so that its inside space is exposed to the extracellular. And then there's a current positive charge flow into the inside. So there is a damage here, which makes the positive current flow outside from the membrane to inside of the membrane. Okay, so that's what they found out. on my hold on, yeah. My- What screen are you looking at? Are you looking at my presentation? Or you're looking at uh my do you see? Okay, let me just so so at the end, Besting considered the cellular membrane as semi-permeable membrane, which means it can be penetrated. Okay, it was not even though at that time it was at that time it was known that the potassium ion concentration is higher in the intracellular, while the sodium ion concentration and chlorine ion concentration are higher in the extracellular fluid. So if you imagine a membrane, the neuron, so there are more potassium inside the neuron rather than and outside the neuron there are more sodium and chlorine. He calculated the equilibrium potential using this equation. Um, and it was of approximately the same as the inject potential recorded experimentally. So he did calculation and he got the same near value to the readings he got from the prop inject the potential in the inject portion. As the inject section is exposed to the intracellular fluid, direct and the indirectly and the intact memory surface is outside of the neuron. So the inject potential can be considered the same as resting potential. So he then proposed his famous membrane theory in 1902. These are the three theories. So the cellular membrane separates the intracellular space from its outside environment, and the membrane has selective permeability to different ions in intracellular and extracellular fluids. So these are about the membrane. So he proposed that there is a cellular membrane that separates axon, the inner inside of the axon from the outer side. Okay, and they have different ions on the inner and the outer side. There is a constant potential difference across the membrane without any stimulus at the resting state. So at the normal condition, so there is a potential difference between the ions. Okay, and this difference increase linearly with absolute temperature. When the cell is activated, the membrane permeability increases dramatically for all ions, especially for potassium ion, and thus the potential difference decrease, and this is the cause of the negative variation. So they managed to find when the cell is activated, when the action potential happens, then there is a sudden there is a sudden increase in ions in all for all ions, especially those inside the axon, the intracellular fluids, which is the potassium ions, which is inside, and this has caused the negative variation where it comes out from the membrane. Okay, so at that point, Bernstein haven't realized on the action potential. He was just looking at the resting state, which means the normal condition. Okay, so That's why, although Bernstein observed the phenomenon, the amplitude of the action potential is much bigger than the resting potential, which contradicts his theory. He neglects his fact, and his theory can neither explain why action potential can propagate along the extent. So even though they come out, they manage to have a good hypothesis on the membranes, on the ions inside and outside the membranes, and the resting potential, but they ignore the action potential and the propagation of action potential along the axons. And this is the gap that is looked into by Alan Lloyd Hopkins and Andrew Fielding Huxley half a century later. So you look into Huxley model later, remember that this is the gap where in which they would try they would like to find out, they would like to solve. Okay, and this is also the reason why they got the Nobel Prize. Okay, another fact that is being ignored by Bernstein, which is not directly stated in the book, it can be kind of stated, but it's kind of indirectly, because Bernstein calculate the potential using Nernst equation, but Nernst equation is only for the case if there is one type of ion with different concentration on both sides of the membrane. So in case of neuronal membrane, we know that there are several different ions with different concentration in both sides. So the Goldman equation should be used. So of course this is known later lah, because Bernstein doesn't know this. Bernstein only knows Nernst equation at the moment, during that moment. Okay, so that's the early discovery. Okay, so on membrane resting potential, but neglecting the action potential, and then people start to move to model. Even with that hypothesis itself, people have started to model neurons, and which is the best object in the nervous system. And the first and this is done by mathematicians. And the first mathematical model was established in neuroscience. By Lapik, 1907, and McCullough and Pitts, 1943. There's a lot of different models that have been developed further, and Hopkins and Huxley model of neuronal membrane is regarded as the founding and classical achievement of computational neuroscience, and it remains the touchstone for neuromodeling until today. Okay, so this is just a brief introduction. So this is Lapik. So his work, we will discuss his work later when we see the simplified neuron model. So from frog to integrate and fire. So because Lapik actually introduced this integrate and fire neuron model, so which is a simplified neuron model. So we'll go through the single neuron model first, which is not simplified one, the full version. Okay, first before we discuss the work of Lapik. And former neural model by McCullough in 1943. So they actually model the neuron into simple artificial neuron. I think you have learned about this neuron with Prof. Putra. So everything this type of neuron comes from McCullough and Pitts. So the inputs can be either a 0 or a 1, as well as the output. So these are the early formal neuron proposed by McCullough Pitts, and they have been used for artificial neural network. Okay, this is the foundation of artificial neural network, and you have learned about this with Prof. Putra. So in this topic is just a theory from how does the neuron comes into uh, this being how does the neuron is being modeled into this what call into this artificial neuron or neural network model. So, this is neural network or circuits. Okay, or circuits. Okay, so that's Magdalene. So going back to Hodgkin. Okay, so that's Lapix, Maculos, and also now going back to Hodgkin. Okay, so Hodgkin and Huxley ionic theory. This is in 1938. Hodgkin did an experiment where he sent axons of crabs and lobster into oil and put one electrode in the section of the axon and another electrode on the uninjured surface of the axon. So they experimented on crabs and lobster. They put electrodes on the axons of the crab and lobster. There are two situations, the injured surface and non-injured surface. And he found that the amplitude of the action potential was almost twice as the resting potential. So when the injured surface means the membrane is torn or something, so there is ions coming out from the membrane. So that's the action potential. So the result definitely indicate that the action potential is not just abolishing the selectivity or permeability of different ions to reduce the resting potential. There is a reverse of the polarity at the membrane potential, which could not be explained by Bernstein theory. So since Bernstein chose to ignore, so of course his theory cannot explain whatever is being observed by Hodgkin in 1938, because Hodgkin actually found out the action potential. Okay, right. Then Hodgkin later learned how to measure the membrane's conductance change during spiking. So this is an important knowledge that he acquired, where he is able to calculate the conductance and come up later with an how to solve how to solve the gap in his model. Okay, so but first when he experiment, he did the experiment. His experiment showed that the membrane permeability to ions was greatly enhanced, but it was still not clear which ions were responsible for conductance increase. Okay, so he's not sure. So that's why he's able to measure, but he is not sure which ions are responsible. So 1939, this is where Huxley joined Hodgkin group, and Hodgkin actually came up with an idea that why not use giant Atlantic split, because it has a giant axon, and where they can put an electrode on the axon without touching the membrane wall. So the membrane wall will not be injured, because before this, when they put the electrode, the membrane is being injured. So there's a like kebocoran, or what is bocor in English. So there would be like bocor in English. There would be like openings on the membrane. So in this case, they will they don't need to touch the membrane wall, so they put the axon there, so the electrode there, and then the nerve fiber was intact except for only a little damage at the end where the electrode was inserted into. So it insert from the end, so it doesn't affect so much. The other electrode was placed in the placing solution so that the electrical activities could be recorded accurately. Okay, so that's why he used the giant the Atlantic split with giant axon, And this is the waveform that they got from the readings in 1939, not 1929, 1939. So the waveform of action potential recorded. Yeah, they got this waveform, which is the action potential. Okay, so unfortunately, the Second World War started in 1939, so they have to stop the experiment, and they continue in 1962 again, where they propose, they describe the ionic mechanism underlying initiation and propagation of action potentials in the split giant axon. So this is what they suggest. Okay, so the overshoot during spiking is the action potential. They consider the fact that the concentration of potassium in the intracellular fluid is much higher than the one in extracellular fluid. On the contrary, the sodium ionic concentration is much higher in the extracellular fluid. So this now they can measure which ion is responsible for the 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 spiking. Okay, so they are able to identify that potassium ions is higher in the higher than the one in the inside potassium ions are higher than the outside potassium ion, and the sodium ionic concentration is much higher in the outside layer of the outside of the membrane. So their hypothesis proposed that the membrane permeability to sodium ions must be much bigger than that of potassium ions during spiking, so that there are more positive sodium ions pouring in than the positive potassium ions leaving out. And the electrical polarity inside the nerve can even be reverted to a positive value near the sodium nurse potential. Okay, so this is what they suggest. Okay, more positive sodium ions pouring to in than the potassium ions leaving out. And we have seen this in action when we discussed how action potential happen. We have seen this, the movement between the sodium and the potassium. Okay, so you can relate to this. And it's important that to note that the permeability of the nerve cell membrane to sodium and potassium ions is not constant, but depends on the voltage of difference across the membrane and the time. So this is what they also observe. They summarize their ideas into an electrical circuit model. Okay, this is the circuit model that they come up with, where of neuronal membrane. So the cell membrane is composed of an impermeable lipid bilayer with embedded proteins in it. So they make an analogy of lipid bilayer as the capacitor. Okay, lipid bilayer as the capacitor. The embedded proteins is symbol as is being represented by several changeable resistors depending on the voltage difference across the membrane and also on the time. So these are the resistors, and the nurse potential is actually a battery. So this is the nerve potential. Okay. What is nurse potential? The ionic concentration difference between the inside and outside of the membrane, and there are the nurse potential of such specific ions across the membrane. The difference between the membrane potential and nurse potential will push the ion to penetrate the membrane in the opposite direction to the one by the concentration gradient force. So this is how the nurse potential happen. How the membrane is penetrate, and the force behind it is the nurse potential. Is initiated by the nurse potential. Right. However, there is a gap where Hodgkin and Halsey assume that there were potassium channel, sodium channel, and some leak channel and the cell membrane. Although these channels had not been identified at that time, so what Hasley and Hodgkin Hasley found out that there might be a leak channel at the cell membrane. So, but they don't know what is the channel. So they had not at that time they had not identified that. But after a century, half century, they were thoroughly verified by patch clamping technique by other researchers. Okay, so these in later years, uh, people are looking into explaining the channels, finding out the channels that being described by Hodgkin and Huxley. Okay, so they not just find out the model neuron membrane model, but they also able to identify that there is a leak channel, that there is a channel in the cell membrane, but they don't know what it is. But researchers after work into finding this, so they provide the gap for other researchers. So as far as the chlorine channel is concerned, this potential is very close to the membrane resting potential. So its effect could be detected at the first approximation. But there is still one problem left with Hodgkin and Hasley model, as there are several different ions inside and outside the cell. The membrane voltage calculated by Goldman equation, which is also the voltage recorded experimentally, is different from the Nernst potentials of this ion. So since there are different ions outside the cell, so even the Goldman equation is giving a different reading than the Nernst potential of this ion. So what happened is for every ion, the force which drive the ion in one direction owing to the conservation gradient cannot be balanced by the electric field force which drives the ion in the opposite direction. Thus, the net flow of ions cannot be zero, and the ions must flow across the membrane in some direction. So, the Nernst potential, it needs to be zero, which is the net flow should be zero, but the ions, but it is not zero. So then how can the resting potential be maintained for a long time? In other words, if the membrane is not absolutely impermeable, then how can the concentration difference of an ion across a membrane be kept? So if you how can we call okay what we call how can you make sure that the resting potential be maintained after the spiking? Then the resting potential need to be maintained for a long time, so that the membrane did not there is nothing being sent across the membrane. So how does uh, the concentration difference of an ion because we need to make sure that the membrane is not permeable, cannot be penetrated. So how can we ensure that the concentration difference between ion across at the inside and the outside is consistent, so that there is no penetration happening. So in that case, they come up with uh, um, they suggest that there is besides the ion channels, there is another specific protein, the so-called ionic pump, which can move the ions from one side of the membrane to the other side against its concentration gradient. So if the action potential happen based on the ion concentration gradients, okay, but this ionic pump it doesn't regardless of ion concentration gradient, the movement can still happen. Okay, the cost is to consume some energy from biochemical reaction. However, the this pump is neglected in the above model. So the Hutkin and Huxley model, this is what they found out. They found out that they know about ion channels, but they also the ion channels is fine. They can explain about action potentials using the ion channels, but they also noticed that there is another movement of ions from inside to outside of the membrane, the other way around, from another channel, and this is called ionic pump, and this is the channel that people look into after this. So this ionic pump, what the character is that it can move ions regardless of the concentration gradient. And this pump is being neglected on the first time, the first proposed model by Hutkin and Huxley. And okay, so the key point, okay, where in their theory, they assume there are potassium channel and sodium channels in the neuronal membrane. Both of the channels have changeable conductance depending on the voltage across the membrane and time, although this channel had not been found explicitly at the time. So these are the channel that they speculate that is there, but they haven't found that. Nevertheless, they try to solve this, okay, this problem, okay, by making sure that how does the potassium conductance and sodium conductance change with the voltage across the membrane and time consecutively. So the easiest way to measure conductance it can be is to calculate using Ohm's law, and the corresponding current and voltage will be given. And to abolish the capacitance component in the current, the membrane potential should be clamped at a fixed value. So they come up with, based on a series of breakthrough of voltage clamp experiment, they develop a detailed mathematical model of the voltage dependent and time dependent properties of the potassium and sodium conductance. So at first, the first model, the first neuronal membrane model, they didn't take into account this voltage problem. Now they suggest this. Okay. So this empirical would lead to development of a couple set of differential equations describing the ionic basis of the action potential. And the ionic current is subdivided into three distinct components: a sodium current, a potassium current, and a small leakage current, chloride ions. Based on the experiment, they were able to accurately estimate all parameters. So these are all this is the models. So they are with all the voltage gauge just now, so they are able to estimate the parameters. Okay, and this is an example that of the potential difference from Hartley and Hodgkin and Huxley model. So as a summary for Hodgkin and Huxley model in 1952, they won the Nobel Prize to both men in the decade later in 1963. And the field of computational neuroscience was launched. And more than 60 years later, the model is still a reference and gave birth to computational neuroscience. So they are the fathers of computational neuroscience. So biophysical neural model based on the knowledge about neuronal membrane, a variety of ion channels at the level below the cellular levels was given. It could simulate neuronal behavior quite accurately, and thus it can give us insight to the underlying mechanism of neuronal behavior. Okay, the biophysical model is so complete and complicated that it can simulate neuronal behavior accurately, and it can give us insights to underlying mechanism of neuronal behavior. But such model is used as a unit to construct a neural network. If it's used to contrast a neural network, then a huge number of nonlinear differential equations are needed, and the simulation is time consuming. Okay, so it's too complex, and so to come up with a neural network model imitating the biophysical neural model, we'll need to use a lot of nonlinear different equations, and the simulation will be time consuming. So in order to construct a model of neural circuit or or the one at higher levels, the underlying mechanism of neuron itself may not be necessary. So only the input or output relationship of the neuron is important. Okay. So if you just want to model the neural circuits, so the whole mechanism is not important. For this reason, a simple threshold-based model have been developed and are highly popular for studying neural coding, memory, and network dynamics. So there's a simpler version. So what we have looked just now is a complicated version, the original version, where it's taken from biophysical neural model, where Hodgkin and Huxley has been trying to come up with a membrane neuron model based on the actual biophysical neural model. Okay, based on real life case, which means that based on the actual neuron itself. So in order to come up with neural circuit, we can use the simplified neural model. So in simplified neural model, there are two classes of simplified neural model, which is one is based on temporal coding and rate coding. The temporal coding is those that proposed by Lapid and also McCullough and Pitts, and rate coding is the one proposed by Hupfield. Okay, just a recap on temporal coding. Okay, remember last class we talked about temporal and rate coding. So temporal coding is where the information carried by the output depends on the timing of its spike frame. That means that if their output is a series of discrete spikes. So this is just spikes, based on spikes. The mathematical analysis of the discrete spike frame is not easy. That's why it is least used in the old days, but revived in the 19th century and evolved as foundation of neural network, where McCullough and Pitts formal neural model was introduced and being used until now. Rate coding, where the output of the neuron is a continuous variable, which include firing rate and or frequency. Such model is easier for mathematical analysis, where because it has good mathematical properties for the sigma function, and these models dominate the neural network studies on previous centuries before the late last century. However, owing to the fact that rate coding does not work in many cases for a living neuron, and it is energy consuming, the spike neural model has been revived in recent years. So the temporal coding is being used because finally people realize that the rate coding does not work in many cases for a living neuron. So it doesn't really reflect the real neuron. So despite the temporal coding is more relevant. So they use till now we are looking at until now the neuroscientists computational neuroscientists are using the temporal coding. Okay. Going back to the integrate and fire model proposed by Louis Lapid, um, even though in 1907 it was not clear how the spike generates, Lapid grasped the key factors about the excitability of the neuron, in which the sub-threshold passive potential will be integrated gradually until reaching a certain threshold, and then a stereotypical impulse will be fired, and its potential restores to its resisting states. Okay, this is the action potential described described again in a different jargon. And then, based on the law of capacitance in physics, he proposed the first equation, the first model. In this model, the refractory period has not been considered. Thus, the fire rate will increase linearly with the stimulating current without bound, but this is not true for a living neuron. So, to overcome this deficit, a refractory must be introduced, and thus the frequency f obeys this formula. This is by Lapage. Okay, the problem with integrate and fire model is it's not realistic enough as the membrane is not an ideal capacitor. Some leak current can pass the membrane, and in the simplest condition, can pass in, and in the simplest condition, that if the voltage dependent channel and transmitter dependent channel are not considered, the membrane can be considered as a parallel circuit with a capacitor and a resistor. So in solution, a modified model called leaky, integrate, and fire model is introduced. So the activities of the leaky, integrate, and fire model can be divided into two phases: the integration of the sub-threshold potential phase and the firing and resetting phase. So this is where the leaky, integrate, and fire state. Okay. And in the leaky, integrate, and fire model, spike occurs when the membrane potential crosses a given reset value. Okay, so this is the reset value, and the spiking happen crosses the threshold, and is instantaneously reset to a given reset value. Okay, so but no bursting mode. So we have no bursting mode, no adaptations, and no inhibitory rebound. So these are the three models coming out from LIF. The output of Link A integrated fire model is a spike train and no central clock synchronous control is needed. Thus, it is more realistic. In addition, its calculation is rather simple and many authors have been interested in such model. Theoretical analysis has hinted that the neural network model with the leaky integrated neural model can carry out almost all the computations that the typical neural network model can do, and it needs much less energy when it is implemented by hardware, and it's also more suitable for simulation of biological neural network. Okay. Then moving into the rate coding, and into the Hopfield model introduced by John Hopfield, the Hopfield model. John Hopfield is an American biophysicist who is also famous for his neural network model. Okay, he induced his neural model as the unit of his network from known biological facts as an example of a realistic simplified neural model, of which the output is its firing rate. Based on some assumption, he used the membrane current is as the input variable and the firing rate of the spike as the output variable in his model, and a frequency coding assumption is implied. His basic assumptions, his model is based on his basic assumptions, where there are two classes of synapse, excitatory synapse and inhibitory synapse. The neural membrane is equivalent to a parallel electrical circuit with capacitors and resistors. The postsynaptic current can be summed up at the axon hillock, and the relationship between the firing rate and the membrane current at the initial segment obeys the law of a sigma function. The transmitter releasing by a presynaptic spike has quantum property. Thus, only a specific quantity of postsynaptic current can be induced. The sensory neuron can produce the outside stimulus into change of the membrane current, and all or none spike will be fired if the membrane potential and the axon hillock reach a threshold. After that, the membrane potential restores to its resting state. So that's the Hopfield model. There are no diagrams or basically it's just equations for Hopfield model. So I'm not going to delve into it more. So you can read more in the book or in any, if you can find other sources. So I'm for this topic. I will stop till this point only. Even in the book there is more more sections below talking about the properties of the neuron models, the monotonicity or something. I will not go through that. It's enough that you understand how does the neuron being modeled into circuits and also artificial neural network. So how is being the artificial neural network has been uh, uh, discussed by Prof. Putra, so I will not go into that. Okay, so I've put some self-study stuff in your e-learning. So it's about conductance-based neural model, which is actually the Huxley-Hodgkin models, the single neuron models. Okay, so you can look at how he described the model to further understand, and you can also read the book. The book is very, very good. It's a nice read. I mean, I could not stop reading because the way it's being written is good. I mean, it's like it kept you want it makes you want to read more and more. Okay, so go back later. You can read this book, and you can even read the previous chapters, which will be coincide with the topics that we have gone through before. But bear in mind that those topics, the sources the contents were gathered from different sources, different resources. So there might be uh, they might not be equivalent or might be contradictory, or I don't think so contradict so much, but maybe you can get further explanation from the book. But for your to study is enough that you read the slides. For this, only for this topic, you can the contents are exactly the same as in the books. Okay, so inside your, am I sharing my e-learning? Inside your, stop sharing. Okay, so you should be you should be seeing this in your e-learning. So we have intro to conductance based models. These are videos in the YouTube which I have found related to you. You can related to our topics and explain about the conductance space model, which is the single neuron models. Okay, and Hodgkin Huxley channel models and speed as a model and the simulation example. And it talk about multi-compartment conductance based model and the parameter fitting of conductance model. So I have chosen this because there are a few more, but I didn't choose that because it's not related to what we learn. So the first three videos is what we learn in single neuron modeling. This the simulation is the real examples of Hodgkin Huxley simulation, which I cannot show. I don't have any resources to show. So multi-compartment is just for further understanding how these models are being used and parameter fittings and how does this model being used. So I hope it will help you to understand neural model more. And after that, you should be able to understand what Prof. Putra have actually gone through on neuron model on his part on the neuron and artificial intelligence. So this portion should bring you to his portion. So so next time, I will for the next round of this paper, this course, I will have to change the flow of the syllabus so that you learn this first before you learn the neural model with Prof. Putra. But it's okay now. So at least you know that this is the theory part first where the neuron is being modeled into circuits, then into artificial neurons, artificial neural network. Okay. All right. So, any question? Any question? Hi. Go ahead. Who is talking? No. Okay. So no more questions. Then, please. I have already opened the submission link for your assignment. So it's going to be closed at 12 o'clock. I mean, at 001 on 20th December. So your deadline is 19, if not mistaken. It will, the link will be automatically closed at 12 midnight on the 19th. Right. So for test next week, okay, please go. It will cover everything that we have learned on my part. It will be 1 to 2 hours online. And then please, the in terms, it will cover overall and might be a bit more on the latest chapter, which is the neural model. Okay. If you want, I haven't come up with questions question yet. So if you want tips, you can ask me near to the date, near to 19th December. So that's all for our class. Then there's a wrap for me. So after this, you'll be continuing with Prof. Putra onwards. The test will be our last meeting for the semester. There will be another test with Prof. Putra. Yeah, so you have 2 tests, 2 assignments in this paper. So my portion is 1 test and 1 assignment. Prof. Putra is 1 test and 1 assignment. Okay, so make sure that you Prof. Putra gave you assignment and test as well. Yep, ask him. Okay, so that's it. So we can wrap our class for today.
Yeah, hi, doctor. Just want to confirm the deadline of the assignment one more time because in the PDF of the assignment instructions is written 11th of December, whereas the learn is on the submission link is on the 20th, right? So I just want to confirm with you.
Okay. Which one do you like? 11 or 19?
19.
Okay. So it's okay. You can still submit until 19 midnight.
Okay. All right. Thank you.
Okay. Okay. Bye.
Thank you, doctor.
Thank you, doctor.
Oh, by the way, in later, I think at towards the end of the semester, there will be a teaching evaluation form for you guys to fill in. So please fill in for both me and Prof. Putra, yeah? Please do that so that we can get feedback on our teaching. Okay? Thank you so much. The final exam will be online as well. The final exam, I'll give you tips later. Ask me when the final exam is closed. Yeah.
Prof,
Yeah.
the test is given by multiple question or essay?
I haven't decided, but I think it's going to be combination.
Oh, combination of both lah. Okay. Okay, thank you, doctor.
The online exam is essay. The test, I haven't decided yet. The online exam is just like the other exams. Okay, all right. Okay, see you guys in 19 December. For test. Take care, you guys. Take care too, Ifa. Okay, that's it. Thank you so much. Assalamualaikum warahmatullahi wabarakatuh, and have a good day, good weekend.
Thank you, Doctor.
Thank you, Doctor.
Take care as well.
Thank you.
Thank you, Doctor.